So we've been talking about electrolytic reactions and what we can start to use them for. One is to be able to make reactive chemicals out of stable compounds. The other is to actually plate out a metal onto a surface. We see this industrially all the time. Your chrome on your sick rims, or your silver plating on a lot of your flatware or plateware that you use in your house. We saw this, I believe, in our chemical and physical properties lab that we did with the brassing of pennies. And so we see this often. A lot of our different jewelries use this process as well. Now the question becomes, is there a way for us to be able to quantify or actually figure out how many grams of metal we're going to be able to plate given a certain amount of time and given a certain half reaction, or a kind of a charge, if you will. And it turns out we can do that. And here's where our buddy Michael Faraday comes on back. And so Faraday's law of electrolysis, the amount of substance produced at each electrode is directly proportional to the quantity of charge flowing through the cell. And so as the charge that we're actually applying to our substance gets greater, if we have more kind of electrical charge going over a course of time, we're going to be able to plate out more metal on our surfaces, or more at each cathode and anode. And so we can actually quantify this. We can actually figure out, using pretty straightforward stoichiometry, how much metal we should expect to see plating out given a certain charge. Now, if we want to use this, we can actually figure out how much material we're going to have form, or we can figure out how much charge we would need to produce a certain amount of material. And so really, these are the two big questions that we can start to ask. And really, it's going to be the same process. It's just, are we starting with a charge, or are we determining a charge and kind of working back from the information as it is provided? A couple of things to keep in mind as we're starting to look at these calculations. First thing you're going to need to do is balance your half reactions, because you're going to need to know how many moles of electrons we're moving per mole of product. And so that's just going to be figuring out your half reaction from our original kind of balanced electrochemical reaction. We're then going to use Faraday's constant, which was at 96,485 coulombs per mole of electron, to figure out the corresponding charge. Okay, well, if this is our substance and we know how many moles of electrons we're transferring, we now know how much charge we need per mole of electron. And then if we know how many moles of electrons we're moving, we can figure out from the molar mass how many grams of substance that would correspond to. A couple things to keep in mind when we say current, or the amps, as it's sometimes referred to in physics. Amps gets the symbol I. It is just a measure of the total charge being transferred in coulombs over a specific unit of time. For us, that's going to be coulombs per second. And so oftentimes our answers might be in seconds or in minutes. If it's a particularly slow reaction, we might put it into hours or days, but that's a pretty straightforward stoichiometric process. So let's look at an example, just to get a feel for this and how we'd start to do this. So if we wanted to know how long it's going to take to produce 3.0 grams of chlorine gas via electrolysis using molten sodium chloride, given our current power supply of 12 amps. And so from this information, we can actually figure out a length of time. And so I think this amps part is going to come in kind of right at the end. We would start with our given. In this case, our kind of useful given is this 3.0 grams. So by starting with our grams, we can change our grams into moles. We now know how many moles of chlorine we're going to have. And then per mole of chlorine gas, we need 2 electrons to turn those chlorine into chloride, or in this case, chloride back into chlorine. And then we know for every 1 mole, it takes 96,000 coulombs to figure out our total coulombs being kind of needed to get our 3 grams of chlorine to come out. Now that we know the coulombs necessary, keep in mind that if we kind of rearrange our equation, we'd multiply time up, and then we would divide our current over. If we now know our charge, our coulombs necessary, we can divide by the current being applied, in this case the 12, to figure out the total time it would take. In this case, it would be 680 seconds, or about 11 minutes, to get 3 grams of super poisonous chlorine gas to bubble off of our molten sodium chloride solution. Another example for you real quick. Technetium is plating a faucet with 0.86 grams of chromium from an electrolytic bath containing aqueous chromium sulfate, if 12.5 minutes is allowed for the plating, what current would we need? And so this is kind of the other type of question you could see. So before we said, okay, we want to get this many grams out, how much time will that take? Now we're saying, here's how much time we're using, what current or charge would we have, what current needs to be applied, or what amperage do we need to use? And so we'd start again with our grams. Grams to moles. Per 1 mole of chromium, if we look, this chromium was an oxidation value of 3, so that means we need to kind of lose 3 electrons, or gain 3 electrons in order to plate out that solid chromium. And then per mole, it is that Faraday's constant. This gets us our current. From our current and time, we'd have to change this into seconds. Current divided by our seconds would then give us our amps being applied. So the 750 seconds is just these minutes into seconds. So we multiply by 60, take our current divided by the time, and we can figure out our amps that we would have to use for our reaction to occur. A couple more examples for you here. Feel free to give these a shot. I'll go ahead and give you a pause the video, give these a shot, see if you can solve them. Should come out to 1.51 grams of silver, 78.3 hours of battery life from our lead battery. If you're having trouble with these, feel free to come and hang out or shoot me an email. I'm happy to work these through with you. I just want to make sure we're getting some good practice problems as we continue to work forward. And so really these kind of types of questions we can start to ask via electrolysis. We got some additional practice problems on some of our handouts. We'll make sure we are solid on this before we move forward.